going to start. Okay, so we will be recording this. And I probably should introduce myself. I'm Pat Wright. I run the Big Data Utah meeting. I also run Utah Geek events, and I put on different events for the community every year. I currently work at Entrada as Director of Database Engineering, and I also do database consulting. If you have any questions on Postgres, SQL Server, MySQL, I can answer most of those things for you. Just anything we need. So if you need anything around that, please let me know. All these recordings we posted on YouTube under Utah Geek Events. So if you just search for Utah Geek Events, you'll find all the meetings that we've done. And this will be available probably in the next few days. It takes me a little time sometimes to get it up there, but it'll be in the next few days. So as we go through this, if I hear any background noise or anything, I'm going to go ahead and mute you, but please try to stay muted. Michael, you can do questions however you want. If you want them to unmute and ask, that's fine.
Okay.
If you want them to put it in the chat, I can raise it for you. It's up to you. But just know that if I hear background noise, I'll try to mute it just so everybody has a good recording.
Yeah, and that's a good point. So certainly throughout the lecture, if you have questions, don't hesitate to post something in the chat. I'm more than happy to interrupt my planned dialogue. So not a problem. All right, all me?
Yep.
All right. Good evening, everyone. Thank you for joining us tonight. I'm really excited to be here. I'm a geek and I love technology. That sums me up pretty simple. Tonight, we're going to talk about kind of the mixture of big data and artificial intelligence. Some of what I tell you, you may already know. Hopefully, I'll share a few things with you that you're not quite aware of. We're going to talk about training models with data. We're going to talk about big data, sort of the good and the bad of big data. We're going to talk about the wild, wild west and what it used to look like and kind of compare that to where we're at today. And then we're going to talk about my favorite subject, and that is breaking into databases. I started programming when I was in junior high school back in the mid-1970s, and we used state-of-the-art teletype terminals. There was no monitor, had a continuous paper feed, and it was hidden back in the back corner of the school where almost no one knew about it, but we had access to it. The funny thing was the school did not have a budget for paper, and so we would take rolls of hand towels out of the men's room, and we would feed that through the machine, and when it ran out, we would turn it over and run it through again. That's where I learned to program. We could write basic programs. You type something into the terminal, and it would type something back to you. Very high tech. It was connected over a phone line to a mainframe computer, which gave us basic access. When I was in high school, they upgraded. This is a more modern version of the teletype terminal. It looks like a typewriter, but it was the same idea. It's a continuous paper feed, and you'd type something into it, and then it would type something back, and we could write basic computer programs. Fun little side story. When I was in high school, I was taking a pre-calculus class, and we were assigned this process that was very laborious. And I didn't want to do it. And we were assigned like 10 questions of this same laborious function. So I went into the computer lab, and having a couple of years on everyone else, I programmed the computer to do my homework for me, which worked great because I got 100%. I didn't miss a single one of them. The teacher found out, and I got reamed. He yelled at me for probably 5 minutes straight. And then when he was done, he said, "Don't ever do that again. That was a great use of technology. Do your own work." All right, from there, I went to punch cards. My first paid computer job was programming a statistical application at a hospital using punch cards. We talk about big data, and this was big data at the time. You had 80 characters. So imagine trying to write a statistical application based on patient data, and the patient data for every patient was limited to 80 characters. Patient ID, patient name, date of birth, diagnosis, prognosis, all this stuff had to fit on 80 characters. That's what we dealt with. At the time, it was high tech. I have a bachelor's degree in general science with a minor in math and a minor in computer science. I have a master's degree in applied information management from the University of Oregon. I've worked in the industry for a very long time. If you count punch cards, that goes back to the late 1970s. So I've been around the block at least once. Currently, I'm the degree chair for the Master's in Applied Artificial Intelligence at Newmont College, Computer Science. As mentioned before, I love technology. Anything technical, I just love to dive into. I just can't get enough of it. When the industry changed, I changed with it. As computers became smaller and faster, I sought out new technologies, and when AI came out, I couldn't wait to get a hold of it. We kept hearing these words about AI for years, but it really wasn't available to us until just recently. And now that it's available, when I say recently, I mean like 10 years ago. It's great to dive in. So my suggestion to everyone, if you want to learn about AI, there are hundreds of websites that provide data that you can model against. And they also provide sample code, which is great. So if you have a particular type of machine learning that you want to dive into, all you have to do is find one of these websites that have these data sets for you, download the data set, follow their sample code, and you're learning AI. To add to that, there are many, many different types of models, and we're going to talk about a couple of them here in a minute. Depending on your industry, you might want to be very selective in the types of AI you implement. And we're going to talk about a few of them, but it's growing so fast that every day it changes. To give you an idea, when we first started talking about building out this master's program at Newmont College of Computer Science, we started hitting all the different websites to see what was available to us. And as we started developing the curriculum, it changed as fast as we could build a curriculum. So everything you learn today is still viable and it'll still be applicable in the future. But just realize the tools are changing so fast and they're adding so many things every day. So we're going to dabble in that a little bit tonight. So just be aware that if you want to play, there's a lot of free resources. Let's build a machine learning model. The code you see in green are just comments. The first couple of lines that we're looking at here are just loading libraries, so we can ignore those. So when you look at the very first command that we've got in there, load data, this particular data set, someone had this great idea that maybe a country's average gross domestic product has some relationship, some sort of correlation to the population's satisfaction in life satisfaction. So we know the GDP of almost every country. We know the populations of every country. So they did these surveys through all these different countries and asked people, how satisfied are you with life? And then they graphed it based on these different models that they had. So that's the data I'm loading here. I downloaded it from the internet. It's available on multiple sites. So I'm loading that data into a data frame so we can manipulate it. The next couple of lines, I'm pulling out X and Y values. And the text you see there, GDP per capita USD, that's the column name of the table. And then life satisfaction, that's the column name of the table. So I'm pulling out data that's in each column and putting them into objects called X and Y values. Then we're instantiating a linear regression model. And then we fit the data. And when we say we fit the data, what we're really saying is we're training the model. So this linear regression model is going to do a bunch of calculations for us under the covers, and it's going to take that data and build a model for us. The very next thing we do is we predict a value. So you may have a country where you don't have a survey, say your favorite country is Fredonia, for all you Groucho Marx fans. If we know their average GDP per person, we can predict how happy the people in that country will be. So we can now make a prediction based on the machine learning model that we just generated here. It's that simple. You are all now masters of machine learning. Is it that easy? Let's find out. This is what's happening under the covers. I don't know about you, but I don't want to do that math. I only know of one person that's probably online right now that would enjoy doing that. So imagine you had to do this every day by hand. It's going to be laborious. You're going to hate it. This is why I programmed our high school computer to do my math for me when I was in high school. I don't want to do this kind of math. I want to just call a function and say, you do all the complex stuff for me. So we have a couple of different things here. This is the linear regression model. This, I keep thinking there's a camera on me, but only cameras on my computer. I'm pointing to the screen. On the far left, where you look at the y equals sigma mx plus b, that's what's happening in the linear regression model that I just showed you, the code that I just showed you. And then we can also look at the error factors. We want to know if this data is reliable or not. We can do other types of functions that are just as complex. Again, we don't want to do those. The nice thing is someone's built these functions for us. Someone that is far smarter than all of us combined has gone in and built these functions where all we have to do is drop the data in and it's going to do this for us. This is what the data looks like. The blue dots represent the life satisfaction of that country. The red line represents the machine learning model's predicted values. I hear something. Is someone asking a question? Okay. When we predict a value, when we call the function that says, give us a prediction, it's using this red line, this predictive model, to give us a response back. So to kind of simplify this, if you go over the x-axis to 45,000 and you go up to where the y intersects with the red line, we're looking at about 6.25. So that's what the predicted value is going to be given back to you. There's a lot more going on here, and this is where machine learning gets a little more complex than just the code I showed you. If you don't understand your data, and you're going to hear me say this multiple times tonight, if you don't understand your data and you don't understand the results, you're going to be missing a lot of details. So let me throw this out to the group, and you can post back in the chat. As you look at this model, when you look at the blue dots, is there anything that stands out to you that you think might not quite be obvious to others? Yeah. For those of you that didn't hear, there's an outlier to the right. On the far right side, there's a blue dot that's way below the red line. That's the United States. So it doesn't quite follow the linear regression, which is interesting. And there's a lot of reasons we could kick around. Maybe it tails off when you get to a certain number. Maybe we're not as happy as we should be. Maybe there's other factors involved.
Top side outliers are?
These ones?
No, the top.
These ones.
Above the 7 line.
This one? I'm sorry, where are you looking?
Above the 7 line. There's like 4 of them that are little outliers.
These?
Yeah.
Yes. That's a great, yeah. So if you didn't hear that, right in the very middle, somewhere between, say, 40,000 and 50,000, most of the blue lines are above the linear regression. So maybe we're using the wrong model. Maybe this isn't a linear regression.
Something that comes to mind for me.
Go ahead, Cam.
Sorry, Michael.
Go ahead.
Something that comes to mind for me with my background in economics is there's such a thing called the law of diminishing returns. It means essentially the more you have of something, the less it means to you. And that would affect the model of being rather than linear, where if I have $1 more of GDP, I have insert slope here of life satisfaction. Rather, if I get 1 more, it means a little bit less than that. And that's going to create kind of a sloped line that becomes less satisfying as you get higher up into those 55,000, 60,000 GDP per capita.
Yeah, absolutely. Thanks, Cam. So what's wrong with this data? Can we make an assumption if we were trying to do this model that was truly representative of GDP and happiness, what's wrong with this collection of data? It's not a linear model. Absolutely. That's one. What else? If we were trying to do this for real, Where's all my data experts?
in one factor analysis.
Yeah, absolutely. We really need more data. This particular survey, it's a sample data set. So we can write it off and say, okay, it's a sample set, fine. It's a small set of numbers. But if we were doing this for real, we would really want to expand this model to be larger. Maybe it's a bell curve. Maybe what we're missing here are the ends and where it tails off. Maybe it tails off like a bell curve. We don't know because we don't have enough data. Another interesting thing we could do is we could do this same survey based on state or city or however else you want to divide up the different types of people you might be able to segregate. You might find different variables that exist within this data. And by modeling more data points, we might get a better accurate depiction of what we're trying to find here. So we went with just an X and Y axis, which is fine. It's a simple linear regression. But we might want to find, as we dig deeper into this, maybe we need more countries. Maybe we need to divide the countries into smaller units. Maybe we need to divide the economic backgrounds. If we asked a whole bunch of poor people that live in the inner city of Detroit, maybe we'll get a different answer than we did if we asked people who live in Salt Lake City. Not to say that's good or bad, but it would give us more data points to really model this out appropriately. I hope that makes sense to everyone, knowing that you're all brilliant data analysts. Anything else you see that we should kick around on this? All right, let's move on. Actually, one more thought. The further away these blue dots are, let me say this again, the more spread out these blue dots are, the less reliable the data. If the blue dots were really tightly packed around that red line, we would have a really good high confidence that these numbers are good. If they spread way out, our confidence level goes way down. One way to visualize this is a couple of different data sets that are visualized in a box plot. The box plot in the very center is a really good data set. The yellow line you see in the very center is the average. The box itself is within the standard deviation, and then the lines that extend out from it are your flyers. Those are the pieces of data that don't quite fit. Kind of like this blue dot on the right, the United States. That would be an outlier that doesn't quite fit in the norm of everything else. The graph on the far left spreads out a little bit. It's not too bad, but we've got some flyers. The lines are flyers that aren't too bad, but then you've got the circles that extend out beyond that are flyers that are even worse than the rest of them. The plot on the right is extremely noisy. There's a lot of flyers, a lot of data that's outside what we would expect to be normal. And so we might have to go through and clean that data before we start using it. Graphs like this are a great way to present your data in a high level view so that you can kind of get some sense of, is this data reliable or not? So when we look at this machine model we just built, right? We just built this really cool machine learning model. We assume the data is correct. What's wrong? What's wrong with this set of code I've got here? It's subtle. You may not see it obviously, but when I start talking about it, you're going to say, oh yeah, I've seen that before. I'll give you a hint. It's creating a false expectation.
It's just that we haven't tested the confidence yet. We just got a prediction.
Yes, that's a big part of it. I'm not sure who said that, but thank you. Okay. What else? What else is wrong with this snippet of code? The false expectation is that it's too clean. Have you ever pulled a set of data from a database and have it be this pristine? I'd say no. And we'll share some examples here in a minute. When you pull data off the internet like this, and you're using these sample codes, it's really simple to just throw a couple of lines of code. We built this linear regression with 6 lines of code. If you don't count the libraries, it's quite unrealistic. The hardest part of machine learning is getting your code right. I'm sorry, not getting your code right, your data right. Getting clean data that is representative of what you're trying to show is the hardest part of machine learning. Once the data is clean and it represents what you want, the code is simple. If nothing else tonight, I hope you take that away, that the hardest part of AI is trusting your data and getting it right. Because as you can see here, the code's easy. Someone's done the hard part for us. Someone already wrote the formula that we get to use, and they probably didn't get yelled at by the math teacher. So here's a great example. If you look at the very last record, number 4, this is just the head of a data frame. The very last record, and I'll give you a real life example. Pat works at Entrada. I used to also work at Entrada. They do, the short answer is they manage apartment complexes. I don't know if that's a good way to describe it, but when you apply for a lease at an apartment complex, they'll do all the background checks and everything to make sure that you're a good risk for the apartment complex. We had people putting in data, say for example, their friends applying for an apartment in the complex, and they've already been approved, but they have to fill out the form. So they want to put in some number that's really high that's going to ensure their friend doesn't get kicked out. And so they just put in $100 million for their salary. We saw that happen in real life. That's bad data. That's going to skew our results. We looked at that one dot that was way out there, the United States. Talk about skewing data. That record that has $100 million salary, that's going to, I doubt anyone has that salary, especially no one named Alex Brown. That's going to skew our numbers in a way that's really, really bad. We've also got values that are empty. In Python, NaN is equivalent to null. So if you've done database programming and you've heard the word null, NaN is roughly the same thing as null. So we have salaries that are null values. What do we do with those in our process? We have to do something with them. We can't just let them linger. Those will pull down our values or cause the machine learning model to crash. If you look over to the other columns, we've got values that don't make sense at all. Like for state, I've never been to the state of invalid. I've heard it's beautiful. Under gender, you may have a whole bunch of different values that you're not anticipating. I don't want to get into the politics, but just realize that they may be different than what you expect. So at some point, we have to go through and clean this data. That's the hard part of machine learning. If we take out that $100 million salary, and it truly is representative of our customer base, we may be skewing the data wrong. I've also seen people put in a number like for salary, they'll put in 42. Where they meant $42 an hour, but they put it in a field where we're expecting it to be a yearly salary. So again, that 42 is going to skew our data in a very bad way. Once you get clean data, machine learning is easy. So one thing we could do, and again, this has implications, we could just go through and say, delete every record that has a null value. We could go through and say, delete every record that has a value above 1 million, just to throw out a number. We could, go ahead. Yeah, it could be.
All of those, you've got a null or an undefined in at least one column on every record.
Yeah, for this set, you're absolutely right. Yeah. And that's part of the problem. Yeah, absolutely. So you might be throwing away data. You're jumping ahead. Thank you. You're throwing away data that might be representative that you need. You might be guessing too low or too high on your query. If you say anything less than 20,000, is that a realistic number for a salary for someone that's applying for an apartment? I don't know. If you say just get rid of data blanket, you might be losing data that's representative of something else you might be looking at. So again, you can't just blindly start blasting data or putting in values that are an average of the standard deviation, right? You got to do more thinking than just that. So this is the hard part. And again, understand your data. Let's shift gears for a minute. Actually, I'm going to go back to this real quick. I worked for a company years ago. This was back in the mid 1990s. And they had it was a small company. There's 12 employees. And they had a program that someone had written for them years ago. And they had various text boxes in this form that they would fill out for their customers. And this was before cell phones. When cell phones started coming out, they didn't know where to put that value. And so some people would put it in the address to form, the field. Some people would put it in the notes field. Some people would put it wherever else they thought it made sense to put it. Shortly after that, the owner of the company came to us and said, "Hey, I want to do a query of every one of our customers that have a cell phone." The assumption being that people with cell phones had more money, and he wanted to market to them. So we thought, well, we could create a regular expression and search every field for something that looks like a phone number, but we wouldn't know if they were cell phones or not. Maybe it's their work phone, maybe it's their home phone, maybe it's their girlfriend's phone, maybe it's some other phone. We really couldn't narrow that down, and we had to tell the CEO, we can't do it. We can tell you what records people have more than one phone number listed, but we can't tell you if they're cell phones. He didn't like the answer, but that was the reality in which we lived in. Again, dealing with big data that's not clean. If your data is in the wrong spot or it isn't properly labeled, obviously you can't do much with it. And at that point, it's just noise. So let me shift gears here a little bit, and let's talk about another really good example of cleaning data. The same company that I worked for that had 12 employees, they published recreation information. If someone was traveling to Salt Lake and they were one of our members and they wanted to find a golf course in Salt Lake, they could just type in Salt Lake for their search parameter, select golf, and we would search the database for any city listed as Salt Lake City for golf courses. There's a problem with that. If you type in Salt Lake City and you search the database for Salt Lake City, you might be missing out on Murray, West Jordan, all these other cities that surround Salt Lake City have golf courses, right? And they're close enough that you could drive there. So we had to come up with a better solution. So we came up with this great idea that we're going to use latitude and longitudes to do these searches. So our first thought was we'll do a radius search. And there's mathematical formulas where you can do a radius search with the latitude and longitude, but it's very CPU intensive. And remember, we're talking about back in the 90s when computers weren't very powerful. And so doing that type of a query was very laborious. So what we came up with is we looked at the outer edges of a latitude longitude, say a 10-mile, what I called radius, 10-mile radius of this latitude longitude search, and we just looked at the outer edges. And we did our query. So really it was a box. And rumor has it that the Earth is round. So in reality, it was a bent square. But that's okay. If we included one or two other properties that wouldn't have not normally been there, that was acceptable. So we thought, great, we'll use this bent square, we'll do a query. But now we have to get latitudes and longitudes of all of our properties and all of the different locations in the United States. It just so happens that the United States Post Office did, and maybe still does, publish a database with every single city, zip +4, and address range within a city block and their latitudes and longitudes. So we thought, great, we'll just buy this database and put it in load it up and we're good to go. It came on multiple DVDs. They were text files that were comma delineated. So it was a lot of data. And remember, we're talking about 1990s here, right? We don't have that powerful of a computer. So we thought, great, they're comma delineated. We'll just load it in the database. It'll take us a couple hours, whatever. We'll get it done, and then we'll have it in a nice format where we can deal with it. So we load all this data. We get in the database and we're thinking really good about what we just did. Remember the conversation we had a minute ago about false expectations? We assumed the federal government would give us good data. Don't make that assumption. We found that there were addresses, for example, in Salt Lake City that were listed as being in Salt Lake City, but had a latitude and longitude that was several hundred miles away. You talk about skewing data. Imagine doing a search for a golf course with data that's skewed that bad. You're going to be including golf courses 300 miles away, and that's not going to look good for us. So we had to find a way to clean that data. How do you clean that data? Let me throw that up to the group. Let me know what you think. How would you clean that data that has records that are that far out of range?
First question to ask is, if you've got two conflicting facts, which one is correct? If it says it's in Salt Lake City, but the GPS data is 100 miles away, which one is wrong, the city or the GPS?
Yeah, exactly. Yeah, and that's a great point. So we got that. We have to determine whether or not that property is good or bad. Its location is good or bad. What else?
Really fun road trips.
Oh, that'd be great. Company sponsored road trips?
Yeah. It says it's over there. I gotta go.
We got to go find out. I'll send pictures. Yeah. What else? Anyone?
Phone calls? I don't know.
Phone calls? Yeah. Could you imagine calling? So you've got a DVD, multiple DVDs of hundreds and hundreds of records with latitudes and longitudes. If we had paid someone to make those phone calls, it'd probably still be doing it. So when I tell you the answer, you're probably going to think, oh, that's obvious. We use standard deviation. So our first thought was, let's create a standard deviation routine. We'll just spin the data. We'll let it cook for a couple days. And we'll be able to throw out all the outliers and just ignore those. So this guy I worked with built a routine that would spin the database, this massive data that we had, and run the standard deviation routine. Little side story is kind of fun. The guy I was working with that did this program found a bug in the Microsoft database for standard deviation, submitted the bug, Microsoft fixed it, and I would have assumed they would have at least sent him a shirt or something, and he got nothing for it, but that's neither here nor there. Anyway, so they got it fixed. So how are we doing on time? We okay? Plenty of time. I told the guy, I says, this is such a big set of data. I have no idea how long this is going to take. Let's pull a sample set of data out. Let's run your routine against the sample set and see how long it takes. So we got our stopwatches out. We started the application. We click the stopwatch. We let it churn. It finishes. We got our calculators out. We punch in the numbers. And I looked at my buddy and I says, according to my calculator, it's going to take 10 years. And he said, yeah, I got 10 years too. Ouch. All right, that's not going to work. But we thought, okay, let's think this through. Maybe if we add some indexes, we can maybe trim some time off. So we did it again. We took our sample set, added the index, ran it again. We got it down to 3 years. So we're like, okay, what else can we do here? So we started thinking in terms of what really matters with our data set. What are we trying to do with our data? One thought was, we're dealing with this radius search, which is really a bent square. We're dealing with this radius search that isn't all that accurate anyway. We don't have to be accurate down to the foot. And the data they gave us was accurate down to the foot with latitudes and longitudes. We didn't need that accuracy. So we thought, well, what if we're accurate to within a city block? Great, let's run it again. We kept doing this. We played this game over and over and over again. We looked for areas where we could adjust the data without significantly impacting what we were trying to do. And this goes back to the conversation we had a minute ago. If you've got a record in there that says someone has a salary of 100 million, what does that mean? Can we live without that piece of data? So in our case, we could live without that piece of data. So we ran it again, and we finally got to the point where we estimated it would take 3.5 days to clean the data. So we ran it. When it finished, we took a timestamp and our original estimate was off by 30 minutes. So that's how close we were to truly estimating how long it would take. So I think that 10-year estimate was probably pretty close. I wasn't going to wait around. Again, clean data. You got to have clean data. If you don't have clean data, nothing else matters. And if it's not clean, where can you trim? There's other types of machine learning, something called clustering. This particular set of data is evaluating leaf sizes for iris plants. And this is downloaded off one of those links I showed earlier in the lecture. You can classify different types of data, and machine learning is really good at clustering data and finding patterns. So this particular pattern, you can train the model, put in a leaf size, and it'll tell you what type of plant it is. You can also use the same technology if you're in the medical field to find patterns for cancer or tuberculosis or some other fun thing, whatever you're trying to do. So the point here is, even though this is a sample for leaves, you could extend this exact same function for tracking medical conditions or anything else you want to try and model. You could try and track shopping patterns. Let's say you work at Cabela's and you've got all the shopping data from all the different types of shoppers that come into the store, age, gender, whatever else you can come up with. You can take all this different data, put it into a classifier, and it'll find patterns that you may not see in the data, and you can then start building marketing models off of these patterns based on the response you get from your unsupervised learning models. So this particular sample, I hate to say it out loud, but this is representative of a real data set, but it's not real. So when you look at an unsupervised model, this is what it'll look like. But I asked ChatGPT, hey, give me an image that looks like an unsupervised. So it is. So it's not real data, but it's representative of what real data would look like. I almost hated to say that outside, but that's, truth be told. But if I had done a real unsupervised model off one of the test sites, that's what it would look like. Great question. You caught me. All right. I think we're right on track for where I wanted to be. All right, let's talk about securing your data. I'm going to shift gears here. My favorite job while working in the real world was breaking into databases. And it was fun. What's that? No. So I'll give you the scenario. It's not as bad as it sounds. Doctors own their data, right? The doctors wanted to integrate with our alert system to notify patients when they had appointments. The patient management software providers didn't want us in there. So they would put up walls to try and block us from getting to the data without using their tools. But because it was owned by the doctor, it was legal. So the doctor would contract with us and we'd have to go in and circumvent the security to get into these databases. And it was really fun. We had some real challenges. Some of them were easy. The sad thing is, and I'll share this as part of the conversation, the worst part of this whole scenario, even the databases that were really, really strong were easy to break into. Medical databases should not be easy to break into. I never failed. The only failure I had came because I ended up taking a job somewhere else and I didn't finish that particular one. And it was like a 3 or 4 year period when I was working there. I was never unsuccessful breaking into a database. Is there a lesson learned there? I hope. If you're the data expert at your company and you're charged with setting up your database and you know that it's really easy to break in, let me give you a scenario. So in the early days of computers, computers were not designed to be secure. If you go back to the original mainframes, they were not designed to be secure. They were designed to process data. That's all they were designed for. As we started building networks, people started adding layers of security. So now all of a sudden we have these layers of security, but as soon as a DBA puts up a really strong wall to keep people like me out, the CEO is going to call them and say, hey, I need to be able to connect this tool to the database to do some sort of data analysis. And the users are going to contact the DBA and say, hey, I need to connect to the database so I can manage user data. Hey, I need to connect to the database. And all of a sudden your beautiful security wall looks like Swiss cheese. Because it looks like Swiss cheese and the DBAs start to lose track of all these holes that they have, breaking into databases is really easy. That's a warning for all the DBAs out there.
Like they say, security is easy. The hard part's letting people in.
Yeah, and that's exactly true. That's exactly the point I'm getting to. Thank you for saying that. Say it again a little bit louder because I want people to hear that.
Security is easy. The hard part is letting people in.
Yeah, I hope you heard that. Security is easy. The hard part is letting people in. Because as soon as you let someone in, you're creating a path for someone else. There was somewhere else I wanted to go with that, and I forgot what I was going to say about it. Maybe it'll come to me. So I want to give you another example. There are ways, so if someone breaks into your database, how do you know they did? How do you know someone broke? You guess, right? It depends.
I have 2 sets of logs that have a 13-cent discrepancy.
Yeah, really.
Anyone have their own enough to recognize that one?
That's right. So let me give you another fun story. Back in the very early days of the internet, it was the wild, wild west. Security was an afterthought. We didn't realize that there were people out there that would break into systems and cause havoc. We just assumed that we were providing services to people and it was a great thing. And look at this great new tool we have. And the same company that I worked for, I mentioned earlier that there was 12 employees. They wanted to publish this recreation information they had online. And this was the very early days of the internet. And so we stood up a server, we built the database, we built the web front end and all this stuff. And it was wonderful. We started to read these articles about people breaking into databases looking for things like credit cards, banking accounts, and emails. Well, we didn't have credit cards, we didn't have bank accounts, but we did have emails. And what they would do is these hackers would download thousands and thousands of emails, and then they would blast market them and spam them with like phishing attacks and stuff like that. So I started thinking, well, we need to secure our data. So I started looking at encryption routines, and at the time they were expensive and hard to come by, because encryption back then was kind of a new thing, at least for this particular model, this use case. So we thought we'll build our own encryption routine. So we did, basically we implemented 3 different types of encryption: character mapping, a perfect shuffle, if you consider a perfect shuffle, and then the Chinese remainder theorem. Really what we did is we programmed an Enigma machine, and only we knew what the keys were. And that was our way of securing the data. But I thought that's not good enough, because if someone still gets in and gets our data, going back to this notion that they're not really secure, nothing's secure, how do I know that someone broke in and accessed our data? So what I did is I created like 3 or 4 different fake accounts. And in those fake accounts, I created emails that only I knew about. So if someone downloaded our database and got the email addresses, and emails start showing up into these traps, I call them encryption traps, I would know that someone got our database. Well, shortly after we did that, shortly after we built this encryption routine, there was an article that came out that said Microsoft has just announced there's this major vulnerability in their database. Check your database. If you find this particular admin account, you've been hacked. So first thing I did is I went to the database and I pulled up the logs, and sure enough, there it was. Boom, someone hacked in and created an administrator account. And I went to the network logs, and there was this great big spike that was equal in size to our database size. So someone downloaded our data. I thought, oh crap, they got us. So I watched those email accounts, those traps that I set, and we never did receive a single email into any of those traps. So I'm certain that that encryption machine was strong enough. So the reason I bring that up, there are articles coming out now that AI is being used to break private public key encryption. It may have already happened, but there's articles saying that that's a possibility nowadays. A lot of your databases are encrypted with a private public key or something of that flavor. And those are going away. So knowing that people can break into your databases, knowing that encryption is going to be broken soon, if it's not already, you need to come up with something to make sure your data is secure. I hope I scared you a little bit.
Well, and one of the things, being a database person, what we try to do is try not to store that data if you don't have to. I mean, there's so many times in so many companies, I have applications over and over again. Oh no, we want to know all this information about our people. I'm like,
Yeah.
no, you don't.
Yeah.
You don't want to say that.
Yeah.
And I go into every company and none of them have archive strategies.
Right.
Like, oh, we have to keep it for 7 years. I'm like, no, you don't. No, you don't. You don't need to know the email that was sent for something 7 years ago that no one's ever going to open again.
Right.
And you're just holding that piece of information. That's part of the security side, is trim down what you have.
Yeah.
So that you're not as much of a risk.
Yeah. There's a lot of websites that say, do you want to store your credit card to make it easier?
Yeah.
And I say no.
Yeah.
Thanks, no. Almost every day we're hearing something about some big massive database that's been hacked and everything's out there. That's what I had planned for tonight. I'm very grateful that you allowed me to come into your homes tonight. I hope you learned something. We talked a little bit about artificial intelligence, a little bit about big data, cleaning data, representing the proper data, understanding your data, keeping your data safe. I hope I hit all the highlights, and I hope you learned something. If there's any additional questions, now would be a great time to fire them off, and I'd love to answer anything that you might want to share.
Yeah, feel free to raise hand or come off mute for a second. I was gonna add one to your lat longitude slide that you had.
Yeah.
I was gonna bring up there too, one of the things, because I remember doing this years ago too as well, it was probably in the similar time frame. We were trying to do a reference search for the zip code, and we had the same problem of trying to figure out the distance and everything, and it was taking too long. So we also just shrunk our distance a little bit and said, no, we're gonna only focus on just this one point or this one area and focus on that. And then we're not gonna reprocess constantly. We're just gonna reprocess once a night or something like that.
Yeah.
Because it's like what you were saying, you were looking for golf courses. Golf courses don't move.
Exactly.
You need to process this data maybe once,
Yeah.
maybe twice.
And then we're good.
You're not gonna need to process it again for a while.
Yep.
So I find that tons and tons of companies right now fall into that trap of real time. They always want to say everything has to be real time, but I'm like, no, it doesn't.
Yeah.
You may only need the data once a night, and that's perfectly fine. Don't force yourself into the real time trap.
Yeah, that's a great point, and that brings up another thought. One of the things that we contemplated when we built this radius search, the bent square, we didn't have Google Maps back then. So we couldn't say, plot the number of miles on the distance, right? We just said, give us a general sense of how many golf courses are in this general area, which worked great for most of our customers. But what if you're in, for those of you that know Utah, what if you're at Solitude and you want to look up a restaurant and you find a restaurant in Snowbird? As a crow flies, that's really short. But if you're going to drive down the canyon, right? So it's not exact, right? And we recognized that it wasn't exact and we were willing to deal with that. But again, that was understanding our data. So yeah, great point.
Now, which part of the 90s was this? Because I remember MapQuest.
MapQuest did exist. Yeah. We actually talked about implementing that. That was after we did this, shortly after we did this. We never did implement it, partly because of licensing and other issues, but part of it was trust and CPU power. We just didn't, for the amount of CPU power it would have taken, we didn't have a confidence level that we felt it bought us much worth at that point. Today, I'd probably do it different, but you're absolutely right. MapQuest did exist. Yeah.
And I remember the USPS data too. That was a thing to get that downloaded and sent to you that way, because that's also another thing is you couldn't just download a file.
Yeah.
See, and when they would update it, they would have to update it maybe every twice a year or something, but they would send you more DVDs.
DVDs, yeah.
And you'd have to do the whole process.
We didn't. We were content with our data. Although on that same note, there was another set of data that we found from the USGS that listed every point on the maps. So if someone wanted to say, I'm at Hoover Dam, find me a golf course near Hoover Dam. It would resolve Hoover Dam to a latitude and longitude and do the same thing. That data came in clean. We didn't have to do anything to that. But the post office data was horrendous. Great. Any other thoughts?
Sure. Good, thanks, everybody. Thanks for joining.
Yeah.
Appreciate it.
It went for about an hour, which was my plan. Thanks, everyone.